Hey, all right, I'm going to try and do something fairly quick here, best as I can. Let's kind of review back through what happens with various charged particles. So if I have a material that is positively charged and I bring it in proximity to this other material that is neutral, then it is possible for these electrons to come float throughout the material and come to the near side edge. And then when I bring this away, those electrons would go back. In fact, let me make that happen here. There we go, they're back. Now, ooh, one more. Okay, now what kind of material that would be? That would be a conductor because the electrons are not bound to each individual nucleus and they'd be able to come to the near side. As opposed to this material, where the electrons, when you bring this positively charged material in close, these electrons all shift together and it makes it, on the right side here, it's going to be a negatively charged surface. This happens because the electrons are bound fairly tightly to the nucleus of each atom, and the electrons essentially just spend more time on that side of the nucleus, making the right side of each atom negatively charged. So this is an insulator, and by doing this, in either case, we are inducing a charge by getting the electrons to kind of shift within the material. If we were to, let's say I go back to the previous slide here, if the electrons actually transfer, if you let it touch or you let it arc, then that would be conduction versus induction. All right. We have the example of an electroscope where if we bring some sort of charged material in close, if it was, let's say, it's like the black rubber rod, then the electrons will come up to the top. I'm sorry, they'll actually get pushed down because the black rod is negative, and so the electrons will get shifted down to the leaves that are down here, and since both leaves are negative, they would in fact separate from each other. The same thing would happen if we were to bring a positively charged rod in terms of the leaves. There we go. And except what's different is that the electrons would be attracted. I can't grab the electrons. Here we go. The electrons would want to come up, and again, the leaves would be positively charged. They would again separate. All right. So now that I've got that, let me start a new slide here if I can, and let's start with some stuff from scratch. So the force that is on two different point charges would be equal to K times Q1 Q2 over R squared, where K is a constant. So K is equal to 9.0 times 10 to the 9th. The units, I barely pay attention to the units myself. They are newtons times meters squared over coulombs squared. And let's see. Q1 and Q2 is the amount of charge that is on each of the particles, measured in coulombs. That's what the C is. It's the amount of charge. And of course, N is the newtons. Okay, so R is the distance between them, by the way. It's measured in meters, always in meters. And so let's move on. Let's look at what the charge of an electron is. So an electron, that is kind of our, actually I did that quite well. The charge of an electron is specifically 1.602 times 10 to the negative 19th coulombs. So it's an extremely small charge, but it's known as the elementary charge because everything is in increments. It is a discrete amount. It is all in increments of that value. So it's either 2 times that or 3 times that or 100 million times that or whatever it might be, but it's all going to be in values of that. Okay, we can also express this equation up here. Let me actually just kind of shift these over. And we can also express this equation in another form. So F equals, I'm just going to write it like, let's see here. No, you know what? I'm not even going to write it like that. I'm going to just say that you can also express this, that there is a symbol that is epsilon naught. It is equal to 1 over 4 pi k, which is then in turn equal to 8.85 times 10 to the negative 12 coulombs squared over newtons times meters squared. We don't use this too much. It's more of a mathematical issue. Basically, we can put this, we can rearrange it to solve for k. I can actually hold on to that. We can delve into that later, more later if we want to. So I'm going to say that that's fairly unimportant right now. It's just there in case you need it. Okay, E field, electric field. An electric field is equal to the force per charge. I'm using a lowercase q. It's known as a test charge. It's basically going to be there just for the purposes of testing what the electric field is at that location. So this Q and this Q, actually more specifically, this Q and this Q can be the same one. And in fact, the way to express it sometimes can be simply this. That it's, sorry, I know it looks like a 9, pretty much the same thing, isn't it? So it's basically a test charge, which means that this is equal to, let's see, the force is equal to K times Q1, Q2 over R squared, all over the little q, the test charge. Excuse me. But remember, if we said that this is the same thing as little q, those cancel. So that means that the electric field is actually equal to K times Q1 over R squared. So the second Q essentially cancels out. It basically means that we're just trying to put an infinitely small test charge at some location to see what is the electric field at that spot. It basically means that given that you're going to put a certain amount of charge there, how much force would be acting on that charge if you were to place it in that location. Trying to move quick here. All right, so if I were to have a positively charged particle, there would be an electric field that radiates outwards away from it. Why? What does that mean? It basically just means that if you were to take a positively charged particle and put it in some location here, the arrows show what direction that they're going to want to go. That's it. That's all it comes down to. So if I were to have a negatively charged, I don't know what I just did. If I were to have a negatively charged particle here, it would have an E field that goes in towards it. I don't know what I am doing. So if I were to put a positively charged particle here, I would want to go inwards towards it. And then each of these two things would be monopoles. And if you notice, we can kind of loop these around, something like this. And it even looks, there we go. Like that is what a dipole would look like. So if I were to put a positive charge here at any point in time, these arrows show the force that would be acting on it in that moment. And that is a dipole. All right, that is my general gist on electrostatics. And there's one last thing I'd like to express, and that's this. That if you were to have 3 charges, I'm randomly choosing positive or negative, and we can give them certain values. So this is a 2, let's say, microcoulomb charge. This is a 4 microcoulomb charge. Those are pretty standard sort of things. And this is going to be, of course, a negative, I don't know, 5 microcoulomb charge. So a typical question might be, what is the amount of force acting on this charge here due to the other 2, right? What is the force acting on this one due to the other 2? So you would have to break everything down into the x and y components, look at the amount of force that is acting between these 2. So these are separating. So this one here wants to make this one go that way. This one here wants to make this one here go that way. So we would have to look at those forces, break them down into the x and y components, add them up, and then it's vector addition all over again. So you would have to look at the distance between them, apply this equation where F equals K times Q1 Q2 over R squared, where in each time that you run this equation, for example, one time, this would be Q1 and this would be Q2. And then the next time you run the equation, this would be Q1 and this would be Q2. You'd have to run it 2 times separately. And that's what you would do. Okay? All right. Hopefully that's helpful. I got to go. Have a good one.